we will continue with the model of the neuron. And then in this one, there was a bias term added. That is, we had earlier, that is UK. It was a summation which you can see. That is J is equal to 1 to M and WKG and XJ and UK. And this bias term was being. Now we'll look at what is the effect of this BK. That is a bias term. That is, if bk is equal to 0, the equation, that is the output, passes through the origin induced by the input, that is a linear combiner output UK, because this UK we are going to call it as a linear combiner output. But if bias is greater than 0 actually, it becomes what? BK is equal to UK plus BK actually, and the line is going to pass above the origin. But if BK is less than 0, line passes below the origin. Now we'll understand why this is happening actually, how with an example input actually. That is, we will take for example one. We'll take for example the input x1, that is a neuron with the input x, one input 1 and the weight equal to 2h. Then what will be the output? It will be the 2x or 2 1 actually. That is basically, if I take weight as 2 and if I vary this one, then this becomes 2x actually. That is, UK will become, if there is only one input, that is 2x actually. Now we will vary the input and then the bias and we will see actually. That is, basically we want to understand why if B is equal to 0, the line passes through the origin. Say if x was minus 1, like what I said, this is UK is nothing but 2, 2x in this case. Therefore, it becomes minus, that is 2 into minus 1, which is minus 2. Now here, if my input is 0.5, then output will become, that is here minus 1, because UK is 2x actually. We have taken one input neuron because it is having x and the weight is 2 actually. That's all. We are just looking at this one. Therefore, here, if the input is 0, the UK is also 0. If the input is 0.1, that is, 0.5, 0.5, it becomes 1 actually. Now you got an idea, that is how we got this minus 2, minus 1, 0 and 1 and the 2. And we have considered BK as 0. Therefore, it becomes what? UK plus BK, where whatever the input that is UK is there, the same we are going to get here. That is, my UK, when it was minus 2 actually, here also minus 2 we are going to get. That is same the line actually. If it is minus 1, here also minus 1 actually. Therefore, when the UK was 0, VK was also 0. Therefore, the line passed to the origin actually. When the bias is 0, that is the linear combiner output is linear to the induced local field, because BK will not have any effect actually. Now we will consider the case where the BK is greater than 0. That is, in this case we will consider plus 1 actually. Now here same inputs, minus 1, minus 0.5, 0, 0.5, and this, as I said, it is 2x, which becomes minus 2 actually. This you got the familiar. Now this BK we are taking it as plus 1. Therefore here it will be what? Minus 2 plus 1, which is going to become minus 1. Next will be minus 1 minus 1, which becomes 0. That is here, if UK is minus 2, UK is minus 2 and VK, this is our VK actually, it becomes minus 1 there actually. Therefore, the line goes, that is, if BK is greater than 0, it goes, because one other thing you can observe is when UK was 2 actually, it is VK is what? 3. Obviously, somewhere it comes and the point comes here actually. Therefore, the line goes above it. That is, when the bias is greater than 0 actually, your when you do the relation between the UK and BK actually, the line goes above the origin. That is this blue line actually. Now we'll consider the case where the BK is less than 0. That is minus 1 in this case actually. Now same here, this is what? Minus 2 and minus 1 actually, because this is, that is when BK is minus 3, you are going to get the minus 1 somewhere actually. Or another example what we can take is when UK was 2 actually, it was 1 actually somewhere. Or when the UK was 1, this one I can point actually. Uh, this VK was 0 actually. It was 0 actually. Therefore, it is correct. That is, now when you observe here the points minus 2, minus 1, 0, 1, 2, and here the points are what? Minus 3, minus 2, minus 1, 0. Therefore, if BK is less than 0, the line passes below the 0. What is our observation here is when we take the bias actually, the points always will be on the line, but the line will do the getting shifted depending on whether B is 0 or B is greater than, sorry, when B is greater than 0 or B is less than 0. That's all. It passes in this, so this same this thing, but slightly above or below depending on that. That is here. Without bias, the decision boundary must pass through the origin. That is, if bias is not there, it passes through this thing. Very restrictive. With bias, the decision boundary can shift depending on whether it is less than 0 or greater than 0. That is, when we have the bias value which is less than 0 or greater than 0, neurons become more flexible. We can move because what we have to do, we have to learn from the data and we have to twist our weights depending on the input what we are going to learn. At that time we can do some little tweaking with respect to the bias also. Anyhow, we have to do the tweaking with the weights also, but this is what it is going to show. That is, bias acts like a threshold actually, which is